Hi students, today I am going to discuss about the atomic sizes. The first thing you have to remember is that atoms are very small. So the direct measurement of the size of the atom is impossible. So we have to resort to indirect methods. We have to assume that atoms are spherical in nature. So then the spherical sized atoms, when they are placed nearby, the distance between the nuclei, that is known as the internuclear distance. So half the distance of this one becomes what is called the atomic radius. So half the internuclear distance between the neighboring atoms, that is known as atomic radius. Now here itself we find that it can be in the form of metals or non-metals. So if they are in the form of metals, you find that in the metallic lattice, that is the solid state, you find the different metal atoms will be arranged in a fixed manner. If you are taking the two close by atoms, the distance between the nuclei, that becomes the internuclear distance. So half the distance of the neighboring atoms in the metals, that is known as metallic radius. The same thing if it is found in non-metals, we refer to as covalent radius, that is, in the case of non-metals, they are bound together by covalent bond. So the bond length is the distance between the neighborhood atoms, and so you find that the covalent radius is half the internuclear distance between the bonded atoms in the molecule. So that becomes what is called covalent radius. Hope you have understood what it is. Atomic radius means half the internuclear distance between the neighboring atoms, whereas metallic radius is particular for metals. So in the metal lattice, that is in the solid state, they are having fixed structures, and then you find that when the neighboring metal atoms, if you check the distance, that becomes the internuclear distance. Half the internuclear distance between the metal atoms in the neighborhood, that becomes the metallic radius, whereas in the case of non-metals, the atoms are bound together by covalent bond. So half the internuclear distance between the bonded atoms in the non-metals, that becomes what is called covalent radius. Coming to the next type, which is known as van der Waals radius. To explain van der Waals radius, I'll take the example of chlorine molecule. You know, chlorine molecule is made up of two chlorine atoms. So that is bound together by covalent bond. So half the internuclear distance becomes the covalent radius. We know that chlorine molecules are always existing in the gaseous state. So one chlorine molecule is separated from another chlorine molecule by a distance different from the covalent radius. Suppose I take one chlorine molecule here and the other chlorine molecule this side. Clear? So then you find that the distance between the neighboring atoms of the non-bonded molecules, that is always greater than this distance. Agree? So this is the internuclear distance in the bonded condition, whereas this is the nuclear distance between the non-bonded atoms in the molecule. So this distance is known as the internuclear distance. in the non-bonded condition. Half the internuclear distance between the non-bonded atoms in the neighborhood, that becomes what is called van der Waals radius. So you find that van der Waals radius is always greater than that of the covalent radius. So suppose the covalent radius of chlorine molecule is given to be 198 picometers. The case with van der Waals distance, that will be round about 360 picometers. What is the covalent radius? Covalent radius is equal to 198 divided by 2 picometers. So that is round about 99 picometers in the case of chlorine, whereas the van der Waals radius will become half the value of 360 picometers. That is round about 180 picometer. So you find that 180 picometers much greater compared to that of the covalent radius. So always van der Waals radius is more than that of covalent radius. So that's much about the size of the atom. Now coming to the trends in the periodic table. Last video I have discussed in detail what happens to the atomic sizes as we move across a period and down a group. Now coming to what is ionization enthalpy. Ionization enthalpy, we have learned that it is the energy required to remove the valence electron from a gaseous neutral atom. And we find that it is related to sizes. As we move down the group, the size keeps on increasing, so ionization enthalpy keeps on decreasing. Whereas across a period, what did we find? The size of the atom keeps on decreasing, and so the ionization enthalpy always increases. Now coming to the next point, that is electron gain enthalpy. First thing that you have to understand is enthalpy is the other term used for energy. Now electron gain enthalpy means the energy that is associated when an electron gets added to a gaseous neutral atom. You have learned that atoms are generally neutral in nature. Upon adding an electron, you find that it will turn into a negatively charged particle. So negatively charged ion is formed, or anion is formed. So that results in an anion. So you find that in all the cases, the addition will not be in the proper manner. So it depends on what is the electronic configuration of the atom. Suppose if you are taking the case with first group element, suppose I take sodium. Sodium, you know the configuration is neon and 3s1. By adding one electron, you have to check whether it is getting more stability or not. So here you find that it will gain one more electron, means it will gain one electron in the atom, becoming neon and 3s2. Evidently, neon 3s2 configuration is more stable from that of the first case. But here you find that electron is not added together as easy as possible. Now take the case with fluorine. Fluorine, you know, it belongs to group 17. Fluorine is an atom with the atomic number 9. So what will be the configuration? It is 1s2, 2s2, 2p5. So 9 electrons are there, and here you find that this is highly unstable because the last orbital 2p is having only 5 electrons. That means it is unstable. By gaining 1 electron, it will become more stable. It becomes F negative with a configuration 1s2, 2s2 to p6. That means this is attaining neon configuration, which is rather stable. In such a case, such an atom has a tendency to add up electron readily and becoming more stable. So this is an unstable atom. So an unstable atom is having more energy. By adding 1 electron, it is becoming more stable, means it has lost the energy. So where did that extra energy that was present earlier go? You find that that is released. Energy is released, and the energy released is known as delta Heg. That is enthalpy of electron gain. So electron gain enthalpy is released in the process. Is it clear? So then you find that group 17 elements have a tendency to gain electrons and become more stable. So by gaining 1 electron, the extra energy that was present earlier will be released, and you find that the energy released in the process will be negative. So when energy is released, the delta H value will be negative. So what do you understand by electron gain enthalpy? It is the energy that is associated when an electron adds up on a gaseous neutral atom. Now take the case with neon, for example. Neon is taken. Suppose neon is taken. Neon has the configuration 1s2, 2s2, 2p6. This is already having a stable configuration. This is the case with neon. It is having a stable configuration. When it adds up an electron, it will become configuration neon, and the next orbital will be 3s1. That means it is getting the configuration similar to that of sodium. So tell me, out of neon and sodium, which is more stable here? You find that neon is stable. So from the stable configuration, this is becoming unstable. That means it has to gain energy, or it has to absorb energy to change into sodium configuration. Is it clear? So in such a case, delta Heg value for neon will be always positive. So what can you find about the trend in electron gain enthalpy? So what is electron gain enthalpy? It is the energy that is associated when an electron is added to a gaseous neutral atom. In some cases, it may result in release of energy. In some cases, it will result in absorption of energy. That is why we never say that electron gain enthalpy is the energy released. It can be either release of energy or absorption of energy. In the case of group 18 elements, which is already stable, such a case, when it adds an electron, it gets a unstable configuration. So from the stable configuration, it is changing to an unstable configuration, means it has to absorb the extra energy. So the energy absorbed in the case of group 18 is always depicted by positive value. So always you find that group 18 elements are having positive electron gain enthalpies, whereas in the case of group 13, 14, 15, 16, 17, you find that the values become negative, and it becomes more and more negative up to halogens. So what is the trend in electron gain enthalpy? When we just check the electron gain enthalpy in periodic table, you find that as we are moving across from left to right, atomic size keeps on decreasing. When atomic size decreases, the ionization enthalpy increases and electron gain enthalpy becomes more and more negative up to group 17 and becomes positive in case of group 18. So this is the trend. So we find that as we are moving from left to right in a period, the atomic size keeps on decreasing. So the ionization enthalpy keeps on increasing. Electron gain enthalpy becomes more and more negative up to group 17. And when it reaches group 18, which is having extra stability, the energy is absorbed there in order to get it converted to a more unstable configuration. Now check the trend when we are moving down the group. Down the group, what all changes happens? Atomic size will increase. When atomic size increases, what can you say about the ionization enthalpy? Ionization enthalpy decreases. Electron gain enthalpy becomes less negative. It becomes less negative as size keeps on increasing. And you find that down the group, metallic character is increasing, non-metallic character is decreasing. So these are the trends that we have learned. Now one more trend is there, which is known as electronegativity. So what is the difference between electron gain enthalpy and electronegativity? Electronegativity is the tendency of an atom to attract a shared pair of electrons towards it. And this is found to be prominent in the case of nonmetals. You know that in the modern periodic table, the first and the second group consist of typical metals, and so the electronegativities will be very less. That means they are electropositive elements. If they are typical metals, in other words, we learned that they are electropositive elements. They have a tendency to lose electrons rather than gain electrons. So electronegative elements are nothing but non-metals. So we have learned that when we are moving from left to right, the metallic character keeps on decreasing and non-metallic character keeps on increasing. And you find that when non-metallic character increases, the electronegativity keeps on increasing and it becomes maximum in group 17. Group 18 doesn't have an attractive power because it's already having a stable configuration. Hope it is clear. So group 18 elements, they will neither be having electropositivity or electronegativity.